Hello everyone. Welcome to today's tutoring session. Uh, this is the first tutoring session. We'll just keep it as a outline session, and you can also suggest what you'd like to do in the later tutorial sessions. So if you can ask me your doubts. You can just give a brief introduction, like why you are taking the course, what is your background, and then we can discuss the questions. Yeah. Yes, I thought you can ask. Yeah. Okay. So, so you would like some demo to be shown, right? Yeah, yeah. Okay. So from next session, we will try to come up with some notebooks. We will try to show a demo of whatever is taught in the class. Yeah, yeah, yeah. So I will try to post a new link for the Microsoft Teams, and so next week onwards, we can use Microsoft Teams. Yeah, sure. You can you can send me a request, and yeah, we can do that. Thank you. Yes, Pankaj. Yes, you can ask the questions. Okay. Is it okay now? Thanks. Okay, so Saikat has asked a question. Uh, why do we call logistic regression as regression and not classification? So you know the for logistic regression, yeah. So for logistic regression, we use the sigmoid function, right? So that function we also refer to it as the logistic function. So what we are trying to do is we want to maximize the probability whether the given example is belongs to class 1 or whether it belongs to class 2. So since we want to classify the example, it is actually a classification problem. However, we are trying to maximize the probability, and so we, as you have seen in class, if our output space is consists of say continuous numbers, so real numbers, so that becomes a regression problem. So this is just the term that is actually a classification task, but since we are trying to match the probability, we say that it is a logistic regression. Is it clear? So Varun has asked what is a confusion matrix. So okay, let me share my screen. Is my screen visible? Okay. So suppose we are given say 100 examples, and suppose our number of classes is 2, say positive classes and negative classes, right? So now what we do is, suppose it is, so it is a classification task whether we predict it as a positive class or a negative class. So what we do is, suppose we construct some table in this way. So this contains our true classes, and this contains our predicted classes. So since there are two classes, so we can have P or N, and we look at our predicted class P and N. So suppose we are given an example and it predicts that it is a positive class, then we'll put it in this cell. If it is a negative class, we'll put it in this cell. So suppose out of 100 examples, so we are given 100 examples, the algorithm says that 60 of those are positives. So these are 60 predicted positive classes. So out of those 60, suppose 40 of those are true positives, that is their actual class is also positive and their predicted class is also positive. So true positive means actual as well as predicted class is positive. So we will put it in this cell. So these are predicted as positive and they are actually positive. So how many of these are negative? 20 of these are negative. So these 20 class examples which are predicted as positive are actually negative. So we'll put it in this. So these are predicted as positive, but these are actually negative. So these are falsely predicted as positive, and we say that these are false positives. Similarly, suppose so we have 100, out of 100 we have 40 more left. So suppose 30 are given as negatives or predicted as negatives, of which say 20 are true negatives and the remaining 10 are false negative. That is, they are 20. Remaining 20 are false negative. They are predicted as negatives, but they are actually positives. So this confusion matrix helps us to see how or it helps us to evaluate the performance of the our classification algorithm. So from this confusion matrix we can see or we can compute the accuracy. So suppose we have to compute the accuracy. So accuracy will be how many of these are correctly classified. So that is these 40 examples are correctly predicted. These 20 examples are correctly predicted. So our accuracy will be 40 plus 20 out of 100. So it is 0.6. Similarly, we can compute the other metrics such as precision or recall using this confusion matrix. Is it clear, Varun? Yes, Shubham. Okay. So, so let us take this confusion matrix. So accuracy checks how, out of all the examples, how many of those you predicted correctly. So if you look at this cell, so we predicted these as positives and these are actually positive. So these are our correctly predicted examples, right? For this cell, we predicted this is negative and these are actually negative. So these are also correctly predicted. So accuracy measures how much of our examples are correctly predicted. So which will lie on this diagonal of the confusion matrix. So in this case, accuracy is 0.6. Now coming to precision. So precision is given as how many out of all the positives that we predicted, how many of these are true positives. Right? So if you look at it, so in this example we predicted 60 of the examples as positives. However, of these only 40 are actually positives or correctly classified as positives and the rest are false positives. So precision in this case will be 40 by 40 plus 20 is 16, which is 2 by 3 or 0.6. And similarly recall measures out of all the positive classes. So this is the recall out of all the positive examples. Out of all the positive examples, how many are actually positives? So this is TP and this is FF. So in this case this is 40 by 60, 0.66. So these are the definitions of accuracy, precision and recall. Now why do we need this? So as you saw, for accuracy we require only the values along this diagonal. So suppose we have say 1000 examples, and out of these 1000 examples, suppose 900 are true positives, right? So 900 true positives. However, there are no true negatives, zero true negatives. Now, since 900 of these are true positives, we will get a very high accuracy, say 900 out of 1000, so 90% accuracy. But it is not a good measure, because it is due to this class imbalance. It shows that this algorithm performs well, which is not the case, because it is not able to predict this true negative correctly. So that is why we require this additional metrics such as precision and recall. Is it clear? Okay. No. So if you look into some papers, so there is actually something called precision recall curve. So what actually happens is, as the precision, so here we have precision and here we have recall. So once the precision increases, the recall decreases a bit. So you must have seen while evaluating functions, or you will see something called area under PR curve or AUPRC. So there is a trade-off between this precision and recall, and this area under the curve, PR curve, it actually shows how good your algorithm or classifier performs. So there is a difference between this precision and recall. Is it clear? Okay, so when we talk about feature size, suppose we have these, suppose we are looking at houses, right? So house can have many features like floor area, or say location, age of the house, and so on. So these sets of you can say features, they identify a house. So what is the floor area, what is the location, what is the age of the house, and so on. So suppose we are using only these three features, we'll say that the feature size is 3. Now when we come to parameter size, so suppose suppose we are, have you gone into linear regression or something? Anyway, there is you will go, I think it will be covered in the next class. So in linear regression, suppose you are given some points and you have to feed a line such that the error of these distances is minimized. So we know the equation of a line can be written as mx plus some c. So m here defines the slope of this line. So you must have understood what is hypothesis space. There could be many lines, right? It can be like this, it can be like this, and like this. So this m controls the slope of the line, which line minimizes this error. So the number of or the length of this m or the size of this m is called the parameter size. So there is in fact some relation. If there are a lot of features, your parameter size will also be high. So suppose we are talking about neural networks. So in that case, even for some say 100 feature size, you can have billions of parameters. So there is a difference between those two. So parameter size, it refers the size of the model or the function that you are learning, and feature size, it shows how many features you are using to describe your problem or describe your examples. Is it okay? Yes. Yes. So, yes, Suraj, you can unmute and ask the question. Okay. Mhm. So it depends on the type of examples you are using, right? So suppose some company is testing out new drugs, say. So they would like to have less number of negative, like false positive cases, right? Because you don't want someone to be, so you don't want an algorithm to say that someone is cured when he's not cured. So in that case, we'll like the number of false positive to be small. So in that case, we will look at this precision recall parameters. So it depends on the example or use case that you have. Mhm. Ah, okay, so I think Balaji asked the question, uh, is there a full automation where we do not interfere the AI method with database method that can explain prediction without human input? Yeah, actually, there are, so Balaji, there are actually something called auto ML models. So we give them the input and it will run a set of models. The, so and it will return the model that gives the best result on the validation set. So representation learning. So suppose we are going to representation learning. Suppose we have some images and we want to suppose do a classification task. A simple whether it is a cat or a dog. So we know the images they are like a 2D matrix or a 3D matrix. Suppose we have a black and white image and it is an M by N image. So the whenever we are giving it as an input to an ML algorithm, we have to pass it as a vector. So what we do is we will just say this is one row, this is another row, and we stack the rows one on top of the other. So we'll have something like an mn dimensional row. So we will pass this row as an input to the learning algorithm and we will get our output. However, you see in images, suppose it is a cat, so it will have some eyes here, it will have some eyes here and some mouth here. So when we are transforming this cat from this shape to a this shape, we will lose the information, like the two eyes should be at the same level, the mouth should be at the same level. When you are doing it, when linearizing it, the information or the spatial information is lost. So that is why what we want is that instead of just simply linearizing it, we want to learn some intermediate representation of this image such that this information is preserved. So this thing, this learning of this intermediate step, this is called representation learning. Similarly, for text, we want to have that similar sentences should be like clustered together. So we want to learn representations such that these method or these properties are preserved. So representation learning tries to learn this representation. So machine learning is we are given some input, and this input can be raw images, it can be these learned representations, and it tries to learn this function between the input and output. Is it clear? Pankaj, you have a question. Good. So, let us go to feature space. So, when we were talking about this house, right? So, we saw that this house has three features, right? Three features. Now suppose we look at the first feature, which is floor area. Suppose it is given in say square foot, so it could be 100, 200, 350, 10, maybe something like that. So as similarly for location, suppose it is given in some kilometers, it will have some values 2, 3, 5 and so on. Similarly for age. So the feature space shows what are the possible values that our features can have? What are the possible values you can have? So it can have numbers of this sort. Age can be like 10, 20, maybe 100, but it cannot be 1000. So feature space shows us what are the possible values of these features. For hypothesis space, so suppose we have some example like this. Say, suppose these are positive examples and these are negative examples. And again, suppose these are positive and these are negative. So for the first problem, we know that we cannot have a separator, linear separator. Like we cannot have something like this or something like this. We need some circular separator. So for this example, second example, we can have just a linear separator. So hypothesis space shows us what are the available types of separator or hypothesis that you can use. So for this, the hypothesis will be the set of these circular separators. For this, the hypothesis space will be the set of these linear separators. Is it clear? Yeah, if you are doing linear regression, it will depend on your M. So for some slope you will have like this, for another you will have like this. But for more complicated, so when you go in SVM, you will have some other parameters other than M. So it depends on different parameters. Yes, sure. Yeah, that is why we try to measure the accuracy or this evaluate the performance of this model, because if the hypothesis space is very high, so if n is say 100, 2 to the power 2 to the n is too large. We cannot search over all the space. So due to the bias, we will only be limited to searching only a small subspace of the hypothesis space, and due to this we cannot have the base model. We will only have the base model related to the inductive bias that we give. Is it clear? Yes, it will reduce the accuracy. So that's why we have this cross validation. So we do something called as hyperparameter tuning. So hyperparameter tuning, it controls how much or what type of inductive bias you want to give. So how much sparse you want your solution to be, or something like that. Abdul? Abdul? Yeah, you can go. So it depends on the problem. So like in this example, so you cannot have hypothesis space which is linear, right? It will not work well. So you can say that you will require some function which separates this in this way, or maybe you can have a combination of some linear functions which separates in this way. So it depends on your problem. Is it clear? So suppose I suppose I say that there is some function f. Suppose f1 is 2, f2 is 4, f3 is 6, and so on. So if I ask you what is f, what will you say? Yes, f is 2x. So here these ones are the inputs, these are the labels, and you are predicting this function f, right? F is a predictor. So in this case your hypothesis space is a function of the form some constant times x. So this is your hypothesis space for this set of examples. So suppose we have f1 equal to 1, f2 equal to 8, f3 equal to 27. So here your f will be x cube. So your hypothesis space will be of the form x to the power some a. So this is how we define the hypothesis space. What is the form of the function? Clear? Yes, data as well as the output. Yes, the computer does not define, because we will just give the algorithm this say 1 and we'll give 2 and 4. So the computer, yeah, you can say the algorithm tries to find this relation. Yeah, you can say that. Yeah. In case of unsupervised learning, we do not have these labels, right? So suppose we have examples of this sort, and some say this. So our hypothesis space will try to, suppose we are looking at clustering, so it will try to form some blobs which are, say, at some distance from the center. So our hypothesis space will be all the circles or say balls which are at some distance. So these all of these could be in the hypothesis space. Is it clear? Yeah, Rupam will upload these recordings and you can get these recordings. So Varun asked when we should stop tinkering. Can you, what did you mean by that? Yes. Uh, what do you mean by more number of solutions? Yes. So in that case, your hypothesis space will be the set of all those solutions, right? So from those, you will get that hypothesis for which your performance is good in terms of say accuracy or error, something like that. Was it okay? So so if we look at this regression problem, so this is one possible hypothesis. There could be some others, right? There could be a lot of hypotheses. But suppose we have this hypothesis. So if we take this as the hypothesis, the error is much higher than this one. So in that case, the algorithm will select the best hypothesis out of the space of all possible hypotheses. Is it okay? Yeah, it depends on the problem. So for this, we are just looking at this slope of the line. So if we go into SVMs, we'll have some bias terms or some other terms. So it depends on your problem or your algorithm. Mm, so it depends. There is no like hard and fast things that this will perform better. It always depends on your problem, how your data is spread. We cannot say surety that it will perform the best for all examples. Thank you. Okay, Balaji. Okay, you're asking when should we stop tinkering. So for that we have these validation models. So what happens is when we're training the model, or suppose this is our training iterations. The training will decrease, training loss will decrease. So we use this validation set to check which model is the best. So the validation set will also have some loss. It will decrease and at some time it will increase. This is referred to as overfitting. I think you will go through it in a later class. So the point where your validation loss is less, we take the parameters at that point to be the perfect parameters for your model. We stop at that point. Yes, Pankaj. Yes, the algorithm will try to minimize your loss, and in doing so, it will get at the best hypothesis for your example. Yes, Subham. Mm. Uh, okay, so which books are given? Can you give their names? Mm. Yeah, you can. I think the Tom Mitchell book is a good book. You can go through that. Otherwise, there is another book called Pattern Recognition by Duda Hark and Starr. So that book also gives a good introduction to many of these examples. Or yeah, I will write this now. You may get the PDFs online if I am not wrong. And there is another book, Introduction to Probabilistic Machine Learning, I think, or Probabilistic Machine Learning by Kevin Murphy. So that is also a good book. You can, once it explains the concepts well. Other than that, I think the lectures are good. It will clear your doubts, and you can go through these topics in addition to the lectures. Yeah, are there any doubts, or you can ask any general question? Sankari has asked, can you explain the difference between validation and cross-validation? So, if we are talking about validation, so here given our data. So this is our complete data set. We will keep some of this data for testing, some of it will be used for training, and the rest will be used for validation. So in this case we will use the validation set to check which are the best parameters for the model. So suppose our data set is small. So in that case we don't have much data for training or testing. So in that case what we'll do, suppose we divide this data into say k folds, and in each iteration we'll use this set for validation and the rest for training. In the next iteration we will use this set for validation and the rest for training, and so on. We will do it for each of these folds. So this is referred to as k-fold cross-validation. Is the difference clear, Shankari? Yes. Because we want to validate our model on all sets of examples we have. So that's why we use k-fold cross-validation if our data set is small. It depends on your. So suppose you are working with images. So images, suppose we have some 100 cross 100 image. So this is a very large feature space. It is on 10 to the power 6 features. In this case, if we have only say 10 images, so our model will not be able to learn well because number of examples is small. So in that case we will go with k-fold cross-validation. Is it clear? No, there is no rule. You can. It's just experimental. So empirically, how much of this do you want to do? So in general, what we do is out of the data, we take 80, 10, 10, or say sometimes we take 50, 20, 10. So this is train test validation ratios. It depends on how much data we have. There is no hard and fast rule like that. Okay. So Pavani is saying, can we say cross validation as a process of simulating the test phase? Yeah, that is right, because our test data is not visible to us during the training state. So that's why we have this validation set. So we want to see how much or how well our model performs on unseen data. So that's why we use this validation set. Can you give some insight into nominal and ordinal variable? So nominal variables are those variables where there is no order, like suppose our number of uh, suppose we are talking about whether it is a cat or dog. We cannot say cat is greater than dog or something like that. But if we have some variable like age, so we know that 30 is greater than say 25. So those are ordinal variables. Yes, Pankaj. Okay. So suppose we have a data set, say students. So we have some features of the students. So they will have age, height, maybe family income, and so on. So their age can be something like 14, 13, 15. Height can be like 150, 160, 145. And family income can be say 5 lakhs, 10 lakhs, maybe 3 lakhs or something like that. So you see these feature, the range of values is in tens, like 14, 13 and 15. These feature, the range of values is in hundreds and this range is in lakhs. So if we use these features like this for our model, so this will dominate the model, because what we do is machine learning is mostly matrix vector multiplication. So this term will always dominate and we don't want it. So what we do is we scale these values. Say if we divide it by the sum of this, so suppose the sum is s, so this will come between 0 and 1. Similarly this will also come between 0 and 1, and same for this. In that case our model will not be dominated by a single feature. That's why we require this feature scale. Is it clear? Yes. Yeah. So each no feature will dominate the other. So there are different types of normalization. I showed only one type. Some normalization they try to make the mean of this column 0. Some try to restrict the range between -2 and 2 or something like that. So there are different types of normalization based on your application. Oh, because you see the range of values is very different, right? So this is in 14, 15, this is this. So we don't want some prediction to be determined only by the family income. We want some combination of all of these predictions or all of these features. That's why we want the features to be in the same range, so that only one feature does not dominate the prediction. Mm. Okay. Yeah, sure. So probability, yeah. When we are talking about probability, we want to, what is the chance of occurrence of that. So suppose of number of occurrence of event x by total number of events c. So this is the probability. When you are talking about likelihood, suppose suppose we have a coin which is, say, it has a probability of head is, say, 0.7 and probability of tail is 0.3. So suppose we toss this coin, say, 100 times. So we want to see what is the likelihood that we get a head after 100 tosses. So given some probability distribution, we are given a probability distribution, we want to see what is the likelihood of an event occurring given some probability distribution. Is that clear? Yes, my screen is visible, right? No, because of, so for the first toss we have a 0.7 chance of getting ahead. For the second, similarly for the second one we have a 0.7 chance. So after 100 tosses, what do you get? It is a head or is it a tail? So what is the likelihood of getting a head? What is the likelihood of getting a tail? Yes. So likelihood is basically, suppose we are given some distribution p, p of, say, x. Likelihood is generally product, say, I equal to 1 to 100 p of xi. So likelihood is a product of these probabilities. No, this is a product, pi. Sigma is the summation, pi. Sijil Francis is asking, how do you represent high bias and high variance in error training set size graph? Can you explain what you mean by size graph? So, okay, I think you want to see, okay, number of training set. Okay. So in general, we have these train learning curves. So for evaluating any machine learning model, we look at these learning curves. So this axis shows the complex complexity could be anything like number of epochs, your size of your model, or say training set size. So in general, and this is your error. So as the complexity increases, the training loss decreases, and as the complexity increases, the test loss decreases up to a point, but after that it starts increasing. Why is this? If the model is less complex, so if the model is less complex, so we have a high training error. That is, it is not able to find a good hypothesis in the hypothesis space. So that means this region has a high bias. Because our hypothesis space is still small and we are not able to find a good hypothesis in this complexity regime. Once we go into this space, the training loss starts decreasing, so it overfits to the training set. So that means the difference for or the error for the training test size, it has a high variance because your training set is large but your test set is small, so it will overfit to the noises in the training set. So this regime is called as high variance. So you can get these bias variance curves from this learning curve. Is it clear? Yeah, okay. So when we are, so this is the complexity of the model. Suppose our model is a simple model. This is the simpler part of the model, and we are not able to find a good hypothesis to feed to the training data. So that means we have a high bias in the model. That instead of searching over all the hypothesis space, we are biased to search only for a small area. That's why we have a large training error. So once we go into this space, our model is fitting to the training error, or it is overfitting. It will try to memorize each of the examples in the training data, but it cannot do so for the testing data because our model only knows how to feed to the training data. So that regime, this region is called the high variance region. Is it clear? Yeah. Yeah. So you said performance system. What is the second part? I did not get that. Okay. So your performance system, critique, and experiments. These are the points, right? After experiment, these are your points. Okay. So performance. So any learning system will give you a model, and you can check what is the quality of your model based on the performance scores. So we have accuracy, error, precision, and all those sorts of metrics. So this shows the performance of your model. So when we go to critique, based on this performance score, it will say whether it is a good model or a bad model. So if it says that your model is not strong enough, it will again ask you to retrain your model. So that is what happens in neural network actually. It looks at your loss, looks at this matrix, and if it is not good enough, it will again retrain the model. So this experiment, I think I'm not sure actually, but it may refer to what sort of examples you want to take. Like not all examples are important. So this will refer to the training set. I think you should confirm with the book. I'm not sure what this experiment means. And generalizer is that given a problem, how does your model perform on unseen data? Because at the end of the day, you don't want your model to memorize your training data. You want it to perform well on unseen new data. So that is the part of this generalization. So that is, I think that is how it can be interpreted. I mean, if someone has a different interpretation, you can proceed. This cycle we will give a recording of this session. Yes. So Shankar is asking what is hyperparameter tuning, when is it used? Okay. So in a later class, we will come upon this algorithm called gradient descent. I think when you are looking into linear regression, you will come to this gradient descent algorithm. So what happens is, suppose your loss function is like this, right? And the minimum point of your loss is at this point. And suppose the loss for your problem at the present stage is at this point. So you want your model to learn the parameters corresponding to this point. So that means your algorithm will make your loss move in this direction, right? So in gradient descent, there are a lot of technicalities in gradient descent. I will not cover those now, but generally you have to decide how large or what step size you take. So suppose you are taking a large step size, so after one iteration it will go up to this, the second it will go up to this. If your step size is small, it will be reverse, so it will go to this, 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 this. Your algorithm will be slow in this case. If you use this, your algorithm will be fast. So that step size, which we call alpha, it is actually a hyperparameter. It uh, it shows how well your algorithm will perform and what are the performance that you want to get. So you have to tune this parameter alpha such that you get a best results. So if you go to neural networks, there will be some other parameters called momentum or batch size. You will go to it in the later part of this course. So this hyperparameter tuning tries to compute using the validation set what are these parameters that we can use. Is it clear? Yes. So for hyperparameter tuning, we have to test it a lot of values. We have to give a lot of values, and the best, suppose the best step size that gives the best result is returned by the algorithm after this tuning. Is it clear? Okay, CGL is asking what is bias variance trade-off. So, so in a lot of the ML algorithms, we will always come upon this phrase bias variance trade-off. So if we look at this learning curve, you see that this region has a high bias and this region has a high variance, but this region has a low bias. This region has a low bias. So, and this region can be said to have low variance. So what happens is, if we overfeed our model, so it will have a low bias, but it will have a very high variance. But if we have a very high bias, that is our model is not able to learn anything, it will have a high bias but it will have a low variance because it will not overfeed to any noisy terms. So there is a trade-off between this bias and variance. So this point is actually the sweet spot where the bias and variance trade-off is minimum. So whenever you are choosing the parameters of the model, it will be corresponding to this point. Is it clear? Yes. This is under fitting. Yes. 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 Low bias. Variance. Yeah. This is the minimum variance. Jyoti. So, so do you want the explanation for this bias variance trade-off or the complete explanation? Okay, I will explain this whole diagram. So, in this learning curve, this the x-axis it represents the complexity of the model that we are learning. So complexity may be like number of parameters or number of epochs or iterations that you have trained your algorithm and so on. This y-axis it refers to the error of your model. So when the complexity of the model increases, your training loss will decrease because your model will fit better and better to your training data. Right. However, when we look at the test set, at first it will decrease because it will have a model that performs well for both the training and the test set, but after some point the test loss will start increasing. This is because we have a model which learns the training data very well, but it cannot do so for the test data. So that region is said to be a high variance region. So the right side of this slide we say that the model overfits to the training data, and the left side it is an underfitting ratio. So that is what we get from this learning curve. Typically we want the model which has the minimum test or validation error, which should be around this region. It should not overfit, it should not underfit. Is it clear, Jyoti? Training error. Yeah, training loss. This is a training loss or training error. Yes. Test, yeah, test loss or validation loss. So whichever set you are using. Yes. Thanks. So Jyoti is asking what is bias and variance. So before explaining bias, we'll go into the hypothesis space. So as you have seen in the lecture, so for n number of features, we can have up to 2 to the n number of models or functions. So our hypothesis space will have this much number of functions. Now we cannot search over this huge space. So what we do is we constrain our machine learning model to search over a smaller space. Due to this, we cannot have a model that gives the best result. It may be much worse than the best result. So this bias, it due to the restrictions that we put on the hypothesis space, it shows how much different it is from the base model. So high bias means we do not have a very good model that performs well on the training error. So for variance, suppose we have some examples like this. Suppose these are positive and these are negative. Suppose we have some machine learning algorithm that learns a boundary like this. Okay, so now suppose some test example comes, say this one. So this will be classified as negative because it lies on the right side of this. So what happened here is this model tries to learn each of the training data, due to which for some unseen data it will have a very high variance, that is it will not perform well for this data point. Now suppose our algorithm learns some model, say like this. So in that case it will have a better chance of so this is not a good example, say something like this. In that case it will have a better chance of classifying this correctly because it is a simple model. It did not overfit to each of the examples. So our variance for this case will be low. So bias refers to the error in your model due to the less complexity in your algorithm. Variance refers to the overfitting that happens to the training set. Is it clear, Jyoti? Yes, yes. Yeah, this is only for those models. I'm just using it as an example. So it could be this large. In general, for no. If we have more than, actually, if we have say 3 classes, suppose cat, dogs, and monkeys, so we'll have 3 to 10 because each of these could be anything, right? So yeah, so it depends on the example. This is just an example that I'm using from the lectures. No. So it depends. So suppose you have n features, x1, x2 up to xn, and suppose each of these features can have say 10 values, say 0 to 10. This can be 0 to 10, 0 to 10. So total number of possible examples will be 10 to the n, right? And this suppose we have num classes equal to 3, say cat, dog, or monkey. So number of possible functions could be. So how will you differentiate these between the three classes? It will be of the order of 3 to the 10 to the n. How will you separate these? Like these could be one class, rest could be other class, and so on. So this we have this y, right, which is the label. So this could be, so we have 10 to the power n rows, and this could be 1 or 2 or 3. This could have one of the values. So overall we will have this much possible number of functions. Yes, until we discuss these equations in the earlier part of the class. So these are shown here. You can go through it in the recording, or it is given in the lectures, I think. So you can go through it. So we'll post these links in the group in the coming days. Yeah, miss the NP, we'll have to give it to the NPTEL people, and yeah, they will post these links. You'll get a YouTube link to these lectures. It will, I think it will be posted in the Google groups, or I will upload it to YouTube, and maybe tomorrow I will post the link in the group. So recall means that, so recall is given by this column. Out of all the positive examples that you have, how many of those did you correctly predict that they are positive? Is it means how much do you recall? So suppose in an exam, how much of the answer or some concept are you able to recall similar to that? False negative, this one. So one is asking what is concept, hypothesis and concept as same. Actually no, concept, suppose suppose we have an example or a data set where we want to predict whether it is going to rain or not. So your concept is will it rain? So that is the concept. So the model will try to learn whether it is going to rain or not. The hypothesis is a function that is learned. So it will learn some function, say f, which will say whether it will rain or not. So concept, based on the concept, some hypothesis is learned. Is it clear? How many? Okay, Atil is asking what is hypothesis space, feature space, instance space. Okay, so hypothesis space, I think, yeah. So suppose we are given this, suppose we are given this function f equal to 1, f1 is 2, f2 is 4, f3 is 6, right? So we can say that our function is something of this form, f equal to 2x. Or in general we can say f is of the form f is equal to c times x. Or suppose, so in this case your hypothesis space will be the set of all functions which are of this form, some constant into some x. So suppose we have some other example, say f11, f28, f3 is 27. So that means your hypothesis space will be some set of functions which are of this form, which is x to t. So this whole space is called a hypothesis space. Feature space, yeah. So suppose we have this example where our floor area, so we have a house and the features are floor area or location. So the features, this floor area can be can have values such as this, location can have values such as this. So this set of values is the feature space, that is what values your feature can take. For example, for instance space, we can have what are the different types of houses. So this will be one house, this will be another house, this will be another house. So all these types of houses will form the instance space. What are the different examples, or what is the data that you have? Okay, so suppose we are trying to predict the price of these houses. So we have some label, say price. So this is say 2.7, I don't know, 10 lakhs, this is 20 lakhs, this is 50 lakhs something. So in this case the concept is the price of the house. Our machine learning model will try to learn what is the price of this house. Is it clear? So concept is what you are trying to do with the data. It depends on the tasks that you have. Okay, RTL is asking how is precision different from accuracy. So suppose we have this confusion matrix, and suppose we have 1000 examples, right? So in that, suppose 900 of those belong to the positive class, and there are no true negatives that are predicted. So if we look at the accuracy, we will get the model with 90% accuracy, which seems good, but it is actually not a good model because it is not able to predict the negatives correctly. So due to class imbalances, uh, your model can, or the performance can be wrong if we look at the accuracy metric. So that is why we look at those other metrics such as precision or recall. I think this is an assignment question, so I cannot discuss this. So generalization, and there is nothing called validation. We talk about a validation set. So validation, yeah. So given a data set, we divide it into a test set and a training and validation set. So we cannot look at the test set because it is not available to us. So what we have, we want to check how good our training, how good our model performs based on the training data. So for that, we use this validation set. Validation set is proxy for the test set, you can say. Generalization is a different concept. So it means even if you are, so as you can see in the learning curve, yeah, even if your model learns all the or memorizes all the training examples, your generalization or its performance on unseen test data need not be good. So this error between the test loss and the training loss, this is said to be the generalization error. So it measures how well your model performs on unseen data. So that is what is meant by generalization. Yeah. Is it clear? Adil? So one is asking what is inductive bias. So as we saw, our hypothesis space can be very large, right? Like, so in this example we have some space of the order of 3 to the 10 to the n, which is very large. We cannot search over all possible hypotheses in this space. So we restrict our algorithm to look into a smaller space or some simpler models. So for that we give some constraint to the algorithm. Say suppose we say suppose for this example we say that we want to look into models of this one. We don't want models of this one. So this sort of constraints or this sort of bias is called an inductive bias. So in this example you can have many separators, right? This is one, or it can have something like this. It's a bit complicated, but we want we always want to find a simpler model. So while writing the algorithm, we'll say that we'll code it that we want a model of this form. We don't want models of this form. We don't want models of this form. So we are telling the algorithm to look into only certain type of separators. So this is a bias because we are saying what sort of functions you should look into instead of all possible functions. So this bias is said to be the inductive bias. Yes, we try to give some constraints. So once you go into specific algorithms like linear regression and so on, you will see that like for linear regression we say that we want our model to be a straight line, or if you go to support vector machines, even then we want our model to be a straight line. But if we go for something others like ensemble learning or something, our model will be a combination of many straight lines. So it will depend on what type of model you are using. uh, base. So we cannot, there is no model that will perform well for all the algorithms, all the problems. So it will vary from problems to problems. Like if we go for image classification, so neural networks will perform well for image classification, but linear regression will not perform so well in that case. Similarly, for other examples, say weather prediction, some other algorithm may work and neural networks may not work. So it depends from problem to problem. Uh, so in these sessions we will try to give you some demo. We will try to give you some visualizations of this. We'll share the notebooks for those. In the course, I'm not sure if in the later assignments they may have some coding, but it will be like uh, you have to code it up and keep the answer in the MCQ format. So we are not designing the assignments, so I cannot say that for sure. But in this session, we will try to give you some demos. Yes, Atil, unseen data and test data are the same thing, because whatever we don't use for training is a test data or something unseen data. Yes, we will share the link for this session. Okay, then so sample. So suppose we have a huge data set of say 1000 say 10,000 examples, but we only use say 1000 of those examples for training. So that is we are using a sample from those 10,000 samples. So the error for that sample is said to be the sample error. True error will refer to the error with respect to the whole population, that is the 10,000 examples. The feature space refers to the different values that your feature can take, like your age can be between 0 and say 90, your height can be between 130 to 200 centimeter, and so all the possible values that your feature can take is it is given in the feature space. So I think if there are no more questions, we can close this meeting. Thank you everyone for attending, and in the next sessions we'll surely try to give you some demos of the algorithms. Thank you.